Welcome to the Lighting Controls Association's online education course, Tunable-White Lighting. I'm Craig DeLuey, Education Director for the LCA. This presentation introduces you to Tunable-White Lighting Control, a powerful opportunity to gain a new dimension of flexibility from LED lighting to support a broad range of applications. This course is registered with the American Institute of Architects. It's a foundational course for NALMCO's CLCP certification exam, and Education Express is recognized by the NCQLP, the Design Lights Consortium, and the state of California. Needless to say, this does not imply endorsement by these organizations. Check out the course at LCA's Education Express to learn more about applicable course credit, the copyright, and our standard disclaimer about this information. For course credit, you can also click the link in the description below to take the complimentary quiz. Now let's get started.
And here's what we're going to be learning today. First, we're going to explore the relationship between light and color to establish the basis of color tuning control. You'll also learn how to match color tunable lighting to appropriate applications and projects. Specifically, we'll introduce the rationale behind tunable white lighting, color basics, the different types of color tunable lighting, hardware and protocols, specification issues, and where to get more information. So let's get started. Color is important in most applications, from ensuring healthy flesh tones in people to facilitating communication, to making sure colors appear naturally or as most people would expect them to appear. In some applications, such as hospitality, retail, groceries, high-end decor, color is critical. What many people don't know is that perception of color is largely dependent on the quality of the light striking it. For the color red to be perceived, it must be present in both an object and the light striking it. But not all light sources are equal in saturation of the colors that combine to make up white light. As a result, the color emission of light sources can have a big impact on how people, objects, and spaces are perceived. The fruit and glassware shown here provides a quick and easy example of this. On the left, we see these items illuminated with light saturated in red and orange wavelengths, which we call visually warm. On the right, we see them under light saturated in blue and green wavelengths, which are visually cool. By changing the light source, we can change what people see. Because of this, the color characteristics of light sources is an important specification decision. But what if we could change the color output of light sources on the fly? The LED and lighting controls revolution has given us just that capability, and it's opening up new possibilities and applications for lighting. With traditional lighting, color was relatively fixed after installation. If you wanted to change the color or shade of white light, you basically had three choices. You could add a color wheel or gel, change the lamp, or install independently controlled warm and cool lamps. This limited color tuning to specialized applications. In contrast, LEDs are compact and inherently controllable, enabling economical color tuning in a compact luminaire, including adjusting the shade of white light, what we call tunable white lighting. This involves a luminaire capable of a change in color output coupled to a compatible control system or device. By making lighting responsive to color as well as light level needs, tunable white lighting technologies provided new value in markets for manufacturers and new applications and tools for designers and users. White tuning allows for changing the color of light from warm to neutral to cool in appearance, which may be desirable for a range of reasons. Such tuning of white light can be used to, for example, provide apparent cooling or warming to a room. This can create psychological effects, for example, using cool colored light to make occupants feel cooler on a sweltering summer day or the reverse. It can be used for mood setting and to suit the preferences of a tenant, owner, or individual user. We can match room finishes, especially when they change on a seasonal basis or when a space undergoes an interior design remodeling or a brand theme change. We can simulate daylight or candlelight to set a mood or match gallery lighting to the works of art on display. We can match the color of daylight in a windowed lobby by, for example, tuning the light to be warmer during early morning and late afternoon, and cooler at midday. And we can also assist with behavioral control or to otherwise signal an activity change. Some classroom studies suggest that the color and intensity of light can be modified to calm or invigorate students or to focus their attention. And finally, we can potentially support human circadian regulation. Because tunable white lighting adds a new dimension to lighting control, it does present a set of trade-offs. Typically, this type of lighting poses a cost premium, more complex luminaire wiring, and a lower efficacy than fixed color sources. More sophisticated controls may be required along with more rigorous specification and commissioning, particularly as LED chips are added for more color-intensive applications. To understand exactly what it is that tunable white lighting does, it's important to take a quick dive into some fundamentals of light and color. The visible light spectrum is comprised of wavelengths corresponding with different colors. The primary colors are red, green, and blue, which lighting folks abbreviate as RGB. Combined, these wavelengths form white light and the basis of color perception. Scientific understanding of how color is perceived led to the development of models, notably the 1931 CIE color space, a graph that maps perceived color on an XY graph as a ratio of red, green, and blue. As shown, white is a region at the center of this convergence. A related color metric is correlated color temperature, or CCT, which describes the hue of a light source and its emission compared to an idealized blackbody radiator at a given temperature. As the radiator heats in temperature in kelvins, its color emission changes from visually warm to visually cool. This is plotted on the CIE color space as the blackbody locus, a curved line expressing a composition of white light under which most people would perceive colors as appearing natural. A warm white light source typically appears orangish white with a CCT under around 3000 kelvins. Saturated with red and orange wavelengths, warm white light makes warmer colors in a space visually pop while also bringing out some flesh tones. A neutral white light source has a CCT of about 3500 to 4000 K. And a cool white light source typically appears bluish white with a CCT above around 4000 K. Saturated with blue and green wavelengths, it makes cooler colors in a space visually pop. Now that we understand the relationship between light and color, we can begin to evaluate color tunable LED lighting options. The first option is full color control. These LED products can produce a huge range of saturated colors as well as white light CCTs via 3 or more separately controlled primaries, for example, RGB plus amber or white. Generally, RGB is the minimum, but some systems use up to 7 or more colors. The LEDs may be monochromatic, producing a single saturated color, or monochromatic with a phosphor to produce a somewhat wider spread of color or white light. This capability makes full color tunable LED lighting ideal for applications such as architainment, but technical challenges have limited use in general lighting applications. A second color tuning option is a pretty simple one. Dim to warm LED products automatically reduce CCT to produce a warmer color appearance during dimming, similar to an incandescent or halogen lamp when it dims, so as to satisfy user expectations. Typically, these products operate at 2700 to 3000 K CCT at full output and gradually decrease to as low as 1800 K or the color of candlelight during dimming. The technology is relatively inexpensive and requires no additional design or commissioning. It is well suited to applications where incandescent dimming is valued, such as residential, hospitality, and restaurant applications. Now we get to tunable white lighting, which is specifically engineered for general lighting applications and is what we're going to be focusing on for the rest of this presentation. Tunable white products offer white light emission that can be adjusted over a range of CCTs. This effect is typically realized by combining separately dimmable arrays of warm, typically 2700 K, and cool, typically 5000 to 6500 K, phosphor-coated LEDs. Relative dimming of these primaries produce a range of CCT values while also allowing light output to be raised or lowered. Other primaries, or colors, may be added to enhance the spectrum of available colors and ensure good color rendering across the range of CCT adjustment. Some tunable white products feature additional dim to warm capability. While some screw-base LED replacement lamps offer tuning as a feature, it's primarily used with luminaires. The simplest approach to providing this capability is to use a warm-cool gamut, where the relative dimming of warm and cool white LEDs produces a linear path between 2 points on the CIE color space graph, thereby producing a range of CCTs from warm to cool. The challenge with warm-cool gamut is any 2 points connect by a straight line that departs the blackbody curve. Light appears to have a natural appearance if its color coordinates fall on the blackbody curve. If the coordinate goes above, the light may take on a greenish tint. If it goes below, it may take on a pinkish tint. Manufacturers design LEDs to emit light at a given point on the blackbody locus within certain tolerances of deviation from the locus. These tolerances are typically based on ANSI standard C78.377, which specifies the range of white light recommended for general lighting with LED products. These tolerances are shown in the graph where we see the quadrangles. There are various solutions to the deviation, one of which is to limit the CCT range and therefore keep the deviation within the accepted range. Yet another approach is to use an area gamut instead of a warm-cool gamut approach. Area gamut is a more sophisticated approach in which the warm and cool primaries are supplemented with one or more additional colors controlled via response algorithms. The result is a tighter adherence of color coordinates to the blackbody curve, as shown in the yellow line in this graphic. We also gain a range of saturated colors that allow the general lighting to be used for communication or to support other uses of the space. As with all lighting and controls, the right solution always begins with what you want the system to do. For general productivity applications, a 3000 to 5000 K range will often be suitable. For circadian lighting, however, the range may need to be expanded to include a very cool 6500 K. Now that we understand tunable white lighting in general terms, we can look at the equipment and protocols used to apply it to spaces. The simplest approach to tunable white lighting is a locally implemented solution with a manual control implemented using a familiar and relatively low-cost dimming method. In this system, an LED driver operates with a color controller and 2 inputs, one for intensity or light level, and the other for color. The components communicate using 0-10 volt signals that are transmitted either using low voltage control wiring or wirelessly. The controller ensures that CCT can be adjusted while maintaining light level. This basic system is relatively simple and economical as an approach to white light tuning, though 0-10 volt is not standardized and as a result it's not very precise. This can produce slight differences in color output between luminaires sharing a space. In a digital system, digital signals are transmitted using low voltage control wiring or wirelessly. When using an open standard or sticking with a single control manufacturer, digital control produces precise, consistent, and scalable CCT control, along with the potential for programming, such as scheduling as well as measuring and monitoring of the connected lighting. Due to the greater capability, typically, these systems are more complex and may impose a cost premium over 0-10 volt. A wide variety of interfaces can front-end these systems. From sliders and buttons to tablets and keypads and software, there are numerous choices for control of light level and color appearance. More advanced manual controls contain preset scenes to support activities. Remote workstations connected to digital systems allow global control, multiple programmable sequences of operation, scheduling, and analysis of retrieved data. Now we get to protocols. A protocol is a set of rules by which devices must be designed in order to interoperate through communication. Tunable white lighting is typically implemented using an LED driver and dimmer that communicate using one of two methods. The first is low voltage wiring using 0 to 10 volt, DALI, DMX, or a proprietary protocol, and the other is wirelessly using Bluetooth, Wi-Fi, Zigbee, and Ocean, or a proprietary protocol. Note that many protocols in the industry are proprietary, meaning they are specific to a single manufacturer. In many cases, these protocols are based on an open standard that was in turn optimized by the manufacturer for its control offering. Now, any discussion of protocols can get pretty detailed, so bear with me on these next few slides. There's a lot of information to share with you. 0 to 10 volt is an analog control signal produced through the voltage on the control wires ranging from 0 to 10 volt in the US. For color changing luminaires, there's typically one 0 to 10 volt dimmer or dimming channel on a larger control system to raise or lower the light level, and a second 0 to 10 volt dimmer or dimming channel to control the color. This is a control protocol originally designed to dim fluorescent lamps, and it's familiar on commercial job sites and fairly inexpensive. It allows one-way communication only, so a driver is not able to report back, for example, that it is failing. The 0 to 10 volt protocol does not specify the relationship between control signal and relative light level, so a small change on a dimmer slide may produce a large change in light output, or the full range of light output could be produced through the top 50% of the slider range. Applications of the 0 to 10 volt protocol for color tuning products include commercial projects where low precision dimming and color selection is acceptable, and where cost and familiarity are key considerations. Incompatibilities can occur among components because the electrical characteristics for 0 to 10 volt devices are not fully defined. 0 to 10 volt systems can also show inconsistencies in light output because of the control wire run lengths. Voltage drop is a common occurrence with low voltage and long run lengths, and this means that a luminaire 10 feet from the dimmer may receive an 8 volt dimming signal, while a luminaire 120 feet away may receive a decayed signal of 7 volts. Although receiving a control signal from the same dimmer, the two luminaires may deliver visibly different light outputs. DALI stands for the Digital Addressable Lighting Interface. Also originally designed to control fluorescent dimming ballast, the controller sends a signal to the LED driver that ranges between 0 and 255 in integers, which an algorithm then translates into light output. While this can be precise and results in consistent color control, note that DALI drivers may be designed for different dimming curves, resulting in different relationships between input signals and light output. The signal can also be slow, so there can be up to a few seconds of time delay between the time the user interface control button is pushed and the lighting reacts. Control wiring can run from a luminaire to another luminaire, or from a sensor to a user interface to a luminaire, etc., in any order. DALI-based color-changing luminaires can be programmed with a computer-based front end, or with a multi-scene preset wallbox user interface, or with a pair of wallbox slider dimmers. DALI control systems can incorporate building automation system signals, as well as input signals from photosensors and occupancy sensors. Depending on the system, CCT and intensity may be programmed to change during the day based on the schedule with user override for intensity and/or CCT. DALI allows limited reverse communication, so there can be some feedback from components to the controller for troubleshooting and status reporting. Applications for DALI-based color tuning include commercial projects where there's a larger building control system managed by facility engineers who can program and monitor feedback from devices. DALI is appropriate for applications where a 2-second time delay between the dimmer control and light output or color change is acceptable. Originally designed for theatrical applications, DMX has the digital capabilities needed to address and send multiple signals to an individual luminaire to control color and intensity of multiple LEDs. There is an almost instantaneous response by the luminaires to the control signal. DMX is capable of two-way communication if this feature is desired and enabled. Daisy-chained wiring is required, which means each device must be wired to the next in succession. A broad range of user interfaces is available, with color precision and repeatability being somewhat dependent on the interface chosen. DMX signals can also be used internally in Tunable-White luminaires using multilingual drivers, even when the user interface is 0-10 volt or DALI. This allows the Tunable-White luminaire to respond very quickly while participating in a DALI system. DMX applications include theatrical, education, houses of worship, and custom or atypical applications that require a very high degree of responsiveness and precision. And finally, we get to wireless. Wireless controls transmit radio control signals from a transmitter on the interface to the luminaire driver through a receiver attached to the driver, luminaire, or lamp. Some receivers can operate on multiple open standard protocols, while others are proprietary and only enable operation with a given manufacturer's products. Wireless control is suitable when the luminaire is new and has a built-in receiver and controller driver, and/or where installing control wiring would be difficult or costly, such as in an existing building. Now that we understand our solution options for Tunable-White lighting, we can begin asking the questions that will inform our specification. Of course, the first step is to identify the owner project requirements. The owner should clearly express the application need. From these requirements, the designer can create a concept for a system that will satisfy the owner's requirements. This will conclude with a fully realized basis of design, including a written control narrative or sequence of operations, covering the expected behavior of each control device based on various inputs. Finally, the designer must identify what training, documentation, attic spares, and other things the owner will need to use and maintain the system. How smooth do changes in intensity in CCT have to be? Light level in CCT should transition between levels smoothly in applications where change happens frequently and where the change is visible to occupants. How precise does the dimming need to be? Some solutions don't tune light level or CCT precisely, though this is often acceptable in commercial applications. What's the dimming range? The minimum level of stable dimmed output varies across different products, with dimming that drops to 1% and lower output typically being more costly. Applications like restaurants, theaters, and the like often require a very low dim level of 1% or lower, while spaces such as offices and classrooms might accept a higher dim level, such as 5 to 10%. Does the product dim to off? The application may require the light source to dim smoothly from its lowest dim setting to off. What's the dimming curve? Drivers and controls are designed with a dimming curve, and their interaction defines the relationship between slider position and light output. This is a very technical subject we won't explore here in detail, but it provides a question to ask the manufacturer so as to ensure dimming is predictable. How quickly do the lights need to respond to the control? A DALI-based system may take 2 seconds to respond, which may be fine for many commercial applications, while with DMX, system response is nearly instant. Does the interaction between the LED driver and the line voltage dimmer being considered produce flicker? Certain combinations of drivers and dimmers can produce visible flicker. The Department of Energy recommends the combination should produce a percent flicker less than flicker frequency times 0.08, and if that information isn't available, to consider a mock-up before final installation. Are all devices in the system compatible and suited to the requirements? Evaluate the driver's dimming performance while confirming its compatibility with the dimmer. At the front end of the system, the user interface is of course very important. It should be intuitive and convenient to use, so it will be appreciated throughout the system's life. Important questions to consider include: how simple or sophisticated should the user interface be? Where does the controller reside? Is it located in place of a wall switch? Is it a handheld remote? Or is it computer software? Can it get easily lost? Does the system require local control only? Or is global control also required? What level of training is required to make programming changes? Are the instructions easy to find if the user forgets how to program the desired colors? How important is it that color performance be maintained over time and matched by another source? Is it possible to test a proposed solution in a mock-up before installation? For many specifiers, DLC listing is important. The Design Lights Consortium recognizes Tunable-White lighting products in its qualified products list, which many rebate programs use to qualify products. To qualify under the latest specifications, light output may not vary more than 20% between any CCT measurement across the full range of the CCT adjustment control signal. The product must be tested at its lowest efficacy setting. So let's wrap this up. Light and color shape perception. Color is dependent on light. Because not all light sources are created equal in terms of color characteristics, we have a responsibility to evaluate and understand color, and we now have a degree of control over color output. Thanks to advances in light source and control technology, for the first time, we can cost-effectively adjust CCT in the field, creating new applications. To accomplish this, we have a range of options for color precision and consistency, various capabilities, simplicity, and cost. The most appropriate choice for a given project will be revealed by asking the right questions about the application. Overall, Tunable-White is an amazing new capability for lighting that offers a new amenity and utility for buildings.
This course is registered or recognized by various industry organizations. This course is registered with the American Institute of Architects. Education credit is recognized by the NCQLP and the state of California, and it's a foundational course for NALMCO's CLCP certification exam. LCA's Education Express is recognized by the Design Lights Consortium in advancing knowledge of network lighting controls, technology, and application. You can learn more about all of this at our website, lightingcontrolsassociation.org. To earn education credit for this course, click the link in the video description to take a quiz. A passing grade of 80% for AIA and 70% for all other recognizing organizations qualifies you for education certificates. Registration with Education Express is required. And now a brief word about the authors of this presentation. We are the voice of the lighting controls industry, a council of the National Electrical Manufacturers Association, formed to educate the public about lighting control technology and application. Our hallmark program is Education Express, a series of web-based courses on a wide range of topics. At our website, you can find this and plenty more, including articles, new product introductions, award-winning projects featuring controls, and more, all at lightingcontrolsassociation.org. Thank you again for attending this course. We hope you found the information useful for your business and wish you success in developing your next project using Tunable-White lighting.